Hello student, I am Dr. S.L. Munde, Assistant Professor, Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in a previous lecture we have seen Cauchy-Gorzac theorem. We have seen complete proof of the Cauchy-Gorzac theorem in last lecture. So in this lecture we will see the last theorem of this unit, that is Schwarz lemma. So we will see the statement of the Schwarz lemma, then we will see the proof of the Schwarz lemma. So what is the statement of the Schwarz lemma? There may be the question in your examination, state and prove Schwarz lemma for the 8 marks. So what is the statement of the Schwarz lemma? Let D equal to is a set Z such that mod Z less than 1, and suppose that f of z is analytic on region D with first case mod f of z less than equal to 1 for z in D. Second, f of 0 equal to 0. Then we have to prove that f dash of 0 less than equal to 1, mod f dash of 0 less than equal to 1, and mod f of z less than equal to mod z for all values of z in D. Moreover, if mod f dash of 0 equal to 1, or if mod f of z equal to mod z for some z not equal to 0 in region D, then we have to show that there exists a constant c such that mod c equal to a, such that f of w equal to cw for all w in D. Okay, so here we have to prove that this is the first part of this theorem, and this is the second part of this theorem. Okay, now we will see the step by step, one by one part of this proof of this theorem. So what is given? So we have given let D equal to a set Z such that mod Z less than 1, and suppose that f of Z is analytic on this set D with first mod f of z less than 1 for z in D, and second is given f of 0 equal to 0. Okay, so this is the given things to for this theorem. Okay, now to prove this theorem, let us we define a function, that is g on a region D in a complex plane C, and it is defined as g of z equal to f of z upon z for z not equal to 0, and f dash of 0 for z equal to 0. So let us we consider equation number 1. Okay. Now from this definition G, it is clear that G is a well defined and continuous for all the points in D except possibly at z equal to 0. Okay. So hence we can consider the limit of this G of z. So taking limit g of z at z equal to 0 for the continuity of g at z equal to 0. So taking limit z tends to 0 to this term, we will get limit z tends to 0 g of z equal to limit z tends to 0 f of z upon z for z not equal to 0. So by using the L'Hospital rule, take the derivative of numerator as well as denominator. So differentiation with respect to z, that is f dash of z upon differentiation with respect to z, that is 1. So by using Leibniz rule we can solve this. Okay. So taking limit at z tends to 0, so put z equal to 0, we will get f dash of 0. So hence we can say that limit z tends to 0 g of z equal to f dash of 0. Okay. But by the definition of the g, f dash of 0 but by the definition of g, f dash of 0 equal to g of 0, z equal to 0. Okay. So therefore limit z tends to 0, g of z equal to g of 0. So putting the g of f dash of 0, that is g of 0 from the given definition. Okay. So therefore by the definition of the continuous function, g is a continuous at z equal to 0. Okay. So if g is a continuous at z equal to 0, z is any point, then we can say that g is also a continuous in region D. Okay, in set D. Okay. Now, by the definition of G, it is clear that G is analytic in D except possibly at z equal to 0, because we have given f is a analytic function. Okay, so by using the definition of the derivative g dash of 0, that is g dash of 0 equal to limit z tends to 0 g of z minus g of 0 upon z minus 0 at z equal to 0. Okay, so by using the definition of the derivative, we at z equal to 0 we can write this step. Okay, now we will put the values from equation number 1, that is g of z and g of 0. So g of z is f of z upon z minus g of 0 is, that is f dash of 0, we already seen, and divided by z is as it is. Okay, so taking cross multiplication, so this can be written as f of z minus z into f dash of 0 divided by z square. Okay, so again here we will apply the L'Hospital rule, because if you put z equal to 0, this will give the 0 by 0 form. Okay, to reduce this, to remove this 0 by 0 form, we will use the L'Hospital rule. So by using the L'Hospital rule, we get limit z tends to 0 f dash of z minus f dash of 0. L'Hospital rule means take the derivative of numerator as well as the denominator with respect to z divided by twice z. Okay, so again if you observe, if you take the z, if you put the limit z equal to 0, so again it will give the 0 by 0 form. Okay, so to remove this form, we will apply again L'Hospital rule. So limit z tends to 0 f double dash of 0, this is the constant term. Okay, so divided by 2. Okay, now we will put now we will take the limit z tends to 0, we will get g dash of 0 equal to f double dash of 0 divided by 2. Okay, but we know that f is analytic on D, so therefore there exists f double dash of 0 is exist. Okay, and hence we can say that g dash of 0 is also exist. Okay, so f double dash is exist, then we can say that g dash of 0 again exist. Okay, so therefore we can say that g is a differentiable function at z equal to 0 and analytic at z equal to 0. We know that every differentiable function is a analytic function. So therefore we can say that, which implies g is analytic in region D. Now we will show. Now from equation number 1 we can write mod g of z equal to mod f of z upon z. From equation number 1 we will take the mod of equation number 1 for z is not equal to 0. We can write in this way. Okay, so what is the mod f of z? We have given in equation number in case number A, that is mod f of z, that is less than equal to 1. So using this we will get mod g of z less than equal to 1 upon mod z for every z belongs to D. Okay, so here if mod z equal to r, where r is less between 0 to 1, so which implies mod g of z less than equal to 1 upon r. So taking limit r tends to infinity, r tends to 1, so it will give limit r tends to 1 mod g of z less than equal to limit r tends to 1 upon r, and which implies take the limit mod g of z less than 1 for all z belongs to D. This is the proof of this second part of this theorem, that is g of z less than equal to. We have proved this part, that is which part? Okay, we will see next. We have to show that mod f dash of 0 less than equal to 0 and mod f of z less than equal to mod z. Okay, we will prove this next part. Okay, so what is next? So to prove this theorem, for we will take mod z equal to 0. If you put z equal to 0, we will get the required result, and mod g of z less than equal to 1. Okay, so 0 is any point in the region D. Okay, so which implies g of 0 less than equal to 1. Okay, but we know that g of 0 by using the definition, that is that is f dash of 0. So putting g of 0 value from equation number 1, definition of the g, so mod f dash of 0 less than equal to 1. Okay, so this is the first result of this theorem. Okay, now we will show that second result. What is second result of the first part? For z belongs to D, where z is not equal to 0 and mod g of z less than equal to 1. Okay, from this equation number 2. So put the value of g of z, that is g of z is mod f of z upon z by the using the definition of the g. So this mod f of z upon z less than equal to 1. Okay. So taking the dividing on multiplying on both sides mod z, we will get mod f of z less than equal to mod z for all z belongs to D. So this is the complete proof of the part number 1 of this theorem. Now we will show that the second part of this theorem. Okay, so we know that. Now let us consider f dash of 0 equal to 1. So by using the second part of the note, f dash of 0 equal to 1, and which implies mod g of 0 equal to 1. So by using the definition of the g, we can write g of 0 equal to 1. Okay, so here 1 is the maximum value of the analytic function g and 0 lies inside D. Okay, so therefore by using the maximum modulus theorem, maximum value of 1 is attained by at a point 0 inside D. So therefore by using the maximum modulus theorem, we can say that g of z equal to constant function. Okay, so therefore which implies g of z is a constant function. Okay, now also let us suppose that mod f of z equal to mod z from the first part of this theorem for some point z belongs to D. Okay, so this can be written as mod f of z upon mod z equal to 1. Okay, and we know that from the definition of the equation number 1, so this can be written as mod g of z equal to 1 for the some points in region D. Okay, so again here, but the 1 is the maximum value of g. So therefore g attains its maximum value at a some point in region D. So therefore by using the maximum modulus theorem, we can say that this g of z is a constant function and hence implies g of z is a constant function. Okay. Now we will prove the last part of this theorem, second part of this theorem. If either mod f dash of 0 equal to 1 or mod f of z equal to mod z for some point z in D, then we get g of z is a constant function. We already seen this in this part. Okay, so therefore g of z equal to, let us we consider constant function, that is c. Okay, taking mod on both sides, so we will get mod g of z equal to mod c. Okay, but we have already seen from this equation number 3 g of z that is 1. So therefore putting g of z equal to 1 in this equation, we will get mod c equal to 1. Okay, so from equation number 4, which gives g of z equal to c, which implies g of z by using equation number 1 by definition of f of z upon z, that is c. So which implies f of z taking cross multiplication cz for all z belongs to g with mod c equal to 1. Okay, so this is the complete proof of the Schwarz lemma. Okay, so this is the very simple proof of the Schwarz lemma. If you read 2 or 3 times, then you can understood very well this Schwarz lemma, and this is a very important exam point of view question. Okay, so dear student, today we have seen Schwarz lemma with a statement as well as the complete proof of the Schwarz lemma. Okay, so with this theorem Schwarz lemma, we have completed unit number 2. Okay, so dear student, from the next lecture we will start unit number 3. Okay, so here we will stop. Okay, so in next lecture we will start unit number 3.